In this lecture, we'll be going over model selection procedures. The reading for this lecture is Chapter 6 in An Introduction to Statistical Learning with Applications in R, titled Linear Model Selection and Regularization. If you have not read this, please pause, go read this, and come back. This lecture will go over three primary topics: how to compare models, the method of full subset selection, and stepwise selection procedures. We begin by talking about how you compare models, and in particular models with different numbers of parameters. Recall from the lecture on bias-variance trade-off that dimensionality in a model refers to a comparison of the number of observations, n, or number of rows, and the number of features or variables, p. And the relative ratio of n to p defines the model's dimensionality, so that as you get larger numbers of feature variables relative to observations, the dimensionality increases. And what this does is it effectively increases the model's flexibility or its variance. So it becomes at risk of overfitting by explaining more variance in the training set that doesn't really generalize to new data and test sets. So as you go from, say, a one-dimensional feature vector here to a 15-dimensional feature set, the 15-variable feature set is going to be much more flexible and at the risk of just basically explaining variability in noise. Now, these flexible models, i.e. models with more feature variables, they'll be good at explaining variability in your training set compared to lower dimensional models really just by chance. And so you want to have a way of accounting for this dimensionality when comparing models with different numbers of feature variables. Remember that with higher dimensionality, what ends up happening is that as you increase model variance, the test accuracy tends to drop in a prediction context. And in particular, as you get more variables than observations, what ends up happening is that there is no unique solution to your problem. You won't find a unique set of reweighting of your feature variables to explain why, and instead you get into this overfitting territory. This also impacts model interpretability. So as you increase variance, you reduce the ability to interpret the specific XY relationships. Essentially what this boils down to is the need to do feature selection, which is determine which predictor variables matter and which are just noise terms or explaining noise. The goal is parsimony here. You want the simplest but effective model possible at both explaining variance in your training set as well as having some degree of generalizability to other data. Now, when you're comparing models, the fundamental problem you face is how do you find this most parsimonious model? How do you find the best combination of feature variables, X, that explain variance in Y? We have discussed in other lectures one way of doing this, and this is the use of validation sets. So you use test error to guide your choice of predictor variables. We went over this when discussing polynomials. So as you increase the number of, let's say, polynomial terms in your model, there will be a point at which your test error stops decreasing and begins increasing. Now your training error will always go down because you'll be explaining just more and more noise terms. But the test error starts to lose its generalizability. So this point at which you have this convexity in the test error is basically your best set of parameters, your best P. Validation is good. It's also costly. It's computationally expensive. So another way to try to understand your optimal set of features is to use something known as a bias adjustment or bias adjusted terms. These are estimates of model error in particular training error, that account for differences in dimensionality, that account for differences in P between models. The idea here is that these are fast. You don't have to compute test sets and training sets. You don't have to do cross-validation. What you just need is a proxy for controlling the degree of variability in your model. You want some way of penalizing your mean squared error term to account for dimensionality. And that's what these bias-adjusted criteria do. We're going to go over 4 different bias-adjusted criteria. They're all essentially variants on a common theme. The first one we'll go over is Mallow's CP. Basically, Mallow's C to the pth power, or pth term. So in this case, P is the number of variables in your data, just like we've always done. And Mallow's CP is the residual squared error from your model plus 2 times P times the variance of Y divided by N. Essentially what you're doing is you're increasing the residual square error estimate by 2 times P times the variance of Y. Remember, you want to minimize the residual squared error. So with Mallow's CP, what you're doing is you're inflating, you're adding in essentially value to the residual squared error as you have larger P. So there's a penalty there. Now, Mallow's CP is somewhat effective, although that just averaging as 1 over n can be tricky. A more popular variant of bias-adjusted criteria is the Akeki information criteria, or AIC. AIC has the same structure. You take the residual squared error plus 2 times P times the variance of Y over, instead of 1 over n, it's 1 over n times the variance of Y. So you have a much larger denominator term, which makes it a larger penalty. Now, this can be rewritten as essentially just 2p minus 2 log L, or in this case, that's the log likelihood of your data from your model. In many cases, this is just the mean squared error term, or the residual squared error, if you're working with normal linear regression. So AIC, the goal here is what it's telling you is the amount of information not accounted for in your model. As AIC gets lower, the amount of variance in Y explained by your model is better. You're losing less information in your model. So you want AIC to be as low as possible. And all you're going to do is you're penalizing the variance that you're reducing by 2 times the number of parameters. A variant of AIC that's a little bit more conservative is the Bayesian information criteria. Although these AIC and BIC both produce pretty much the same results. BIC is essentially the residual sums of squares plus the log of the number of observations in your data set times P times the variance of Y. So notice we just replaced the 2 in our AIC with log n. And we divide that by 1 over n. This can be rewritten as, at least in the normal linear regression context, as P log n minus 2 log L, or P times the log of the number of observations minus 2 times the log likelihood. As with AIC, BIC reflects the amount of information lost in your data. So smaller is better. Mallow's CP, AIC, and BIC all have that common reflection. You want to have it as small as possible. A final adjusted criteria, or bias-adjusted criteria, is the adjusted R-square. This is a variant of the traditional coefficient of determination, except that you're adding in different degrees of freedom to the estimate. So the traditional R-square is 1 minus the residual sums of squares over the total sums of squares. But now you're adjusting your residual sums of squares by dividing it by n minus p minus 1. So the dimensionality of the problem is in a denominator term that adjusts your residual squared error, and your total squared error is just the degrees of freedom of your observations, n minus 1. In this case, unlike the information criteria or Mallow's CP, higher values of adjusted R-squared are better. So the goal here is to maximize that. It's going to be harder to have a larger R-square with models with larger P. In each one of these cases, these are just criteria that take model complexity into account, that take the number of variables in your model into account when returning an estimate of model error. You don't have to do validation. It just tries to use some adjustment of the model error estimate that accounts for the number of terms in your model. Now, why these are useful is that you can now compare lots of models together relatively quickly. You can compare a set of models without having to run a full cross-validation analyses for all variants of your model. You just run different models and compare their adjusted information criteria or adjusted R-squared. That complete set of model comparison gets us into just the general model selection and model comparison methods. And the first one we're going to discuss is something known as full subset selection, sometimes just called subset selection. The main question that selection methods, full subset selection method in particular, ask is, what factors are relevant? What are the variables that are most relevant for your model? And in particular, how do you find the most parsimonious model? How do you just select the most important variables and get rid of the unimportant variables? So let's say I have a regression model like this. So I have P feature variables. What you do with full subset selection is you ask, what is the best combination of variables that provides the best explanation of your data after accounting for model complexity? Essentially what you do is you try to approximate the holdout set variance bias trade-off test, but instead of using cross-validation on every combination of your model, what you do is you try all possible permutations of your model form using all the variables or all combinations of variables 1 through P, but then use the bias adjusted criteria to do your selections. You just use bias adjusted criteria to compare your models because they're going to have different complexities. It's probably easier to think about this by example. So let's say I have a three-dimensional model. So I have my intercept term, and then I have three x's, x1, x2, x3. The number of model variants that I can have of this form or from this model are 2 to the order p. What I mean by that is that if I have three variables, x1, x2, x3, there are 2 to the p number of models that I can compare. So for example, the first and simplest model that I can look at is just the intercept only model. This is the case where p equals 0. I could also compare just the model with x1 against the model with just x2 against the model with just x3. Now the degrees of freedom of these models is p equals 1 because each model just has one x term. I also can compare the model of x1 and x2, x1 and x3, x2 and x3. These are all the cases where p equals 2 because I'm including two x terms in the model. And the final model that I can compare is the full model that includes x1, x2, x3. So these 8 models, 2 to the third, are all possible combinations of models that I can use with variables 1, 2, and 3. And what you do with full subset selection is just run each one of these models, get a fit, look at, let's say, an information criteria. I'll use AIC as an example. And ask, which has the lowest AIC? Because remember, with AIC now, it's easy to compare models that have different dimensionality. If this was my results here, I would say that this fourth model, which is this model here, is my winning model. It is the model that best accounts for my data in the most parsimonious way. After accounting for model complexity, this is the best I could do. So with full subset selection, it's the most comprehensive way of comparing all variants of your model. And as you add in interaction terms, if we're just looking at main effects here, but if we started looking at interaction terms, that complexity explodes really quickly. But the idea with full subset selection is just brute force, compare all variants, and use information criteria to tell you which one is best. This tends to break down, however, in cases where p gets really large. Because remember, you're comparing 2 to the p number of models. For p equals 3, we're already at 8. If p was 13, with interaction terms, it would take a long time to run these model comparisons. So, an alternative to full model selection is to use stepwise selection instead. Stepwise selection methods have the same logic as full subset selection. Use bias-adjusted criteria to compare models with different complexity. But instead of comparing all possible models, you structure the way you compare models. So for example, with forward stepwise selection, what you do is you build up from the simplest model and run an evaluation at every step of p. So essentially what you're doing is for every degree of model complexity, from P1 to P2 to P3 to P4, you run a test, ask what variants of the model in that stage are relevant, and then increase the complexity. Add one more term, compare in that stage, and do it again. So for example, if we still had our 3-variable model here with x1, x2, x3, forward stepwise selection, we'll have to select 1 plus p times p plus 1 divided by 2 number of models. I'm going to keep that equation up there. It'll be more relevant when I get to the end of the lecture. So if I was going to do a forward stepwise selection here, what I would do is first just run the intercept-only model. This is the case where p equals 0. Now, in this case, there is no alternative model, so what we're going to do is we're going to keep the intercept term. Then what we're going to do is we're going to run 3 models with a dimensionality of p equals 1. This is a model with just x1 and the intercept, a model with just x2 and the intercept, and a model with just x3 with the intercept. We compare their information criteria or their bias-adjusted criteria. We let them say which of these 3 is relevant. Let's say, hypothetically, that this x1 model is the best model out of these 3 comparisons. So what we do now is we evaluate a slightly more complex model. We change p from 1 to 2, but we only include models that have this x1 term. We get rid of all models that don't include x1. So now in this next stage, all I'm comparing is 2 models. I'm comparing the model where I have x1 and x2 and a model where I have x1 and x3. And again, I ask, of these 2 models, which one has the best information criteria? Which is the lowest AIC or BIC or the highest adjusted R-squared? Hypothetically, let's say this is the winner. Then what I would do is I would move to the more complex model, which in this case is easy as the last model, and it has to include x1 and x3. Remember that with the full subset selection method, I've ran 8 models. With this one, I've run 7. So I've reduced my number of models by 1. Now, to choose your best model, you evaluate based off of the best information criteria for each heat or each stage. So you look at the model with p equals 0, the intercept only. You ask what was the best performing model when p equals 1. You take that AIC, then you ask what was the best for 2. And you select based off of the best reporting model for each stage. In this case, the winning model is the model that was in the second stage. So the one with x1 and x3 in your terms. Now, this is the forward stepwise version. You can also just invert the process, which happens to be named backward stepwise selection. In this case, you just do the opposite. you start with the most complex model, and then you keep reducing the complexity of your model in each heat. But the logic works just like forward stepwise selection. So in this case, again, we're going to evaluate this model with 3 feature variables. We're going to compare 1 plus p times p plus 1 over 2 models, which in this case would just equal 7. But we'll start backwards. We'll start with the most complex model and say, test the full model. And since this is the only model in this heat with p equals 3, what we're going to do is we're going to carry over all the terms. Now we're going to compare all possible subsets. So in this case, we're going to compare all models with only 2 terms. So a model with x1 and x2, a model with x1 and x3, and a model with x2 and x3. Then what we're going to do is, if this is the winning model, let's say that of these 3, the model with x1 and x3 returns the lowest information criteria, then we're only going to compare the next least complex or less complex models that include either x1 or x3. So this gives us 2 models, just a model with x1 and a model with x3. We'll ask which one wins, and this might be the winning one. And then, of course, we reduce it by going down to the least complex model, which is just your intercept-only model, when p equals 0. And just as before, what we would just do is we would say, okay, of these heats, when we worked backwards from p equals 3 to p equals 0, which one has the lowest information criteria overall of the best performing models in each one of these heats? And, again, it might be this model here, which is the one with both x1 and x3. The idea of forward and backward selection is that in some ways, if there's not that big of a difference between models at a particular stage, then you might have a slightly different set of features at the end when you're using a backward stepwise selection than a forward stepwise selection. Sometimes you might want to think about using them both together. Now, the beauty of these model selection routines, whether we're talking about full subset selection or stepwise selection, is that they allow for you to directly ask, what are the most relevant features that I need for explaining why? What are the meaningful terms in my model? It's an alternative to a hypothesis test in some ways. So for example, let's say that I was trying to ask if risk aversion is associated with childhood trauma, parental income, psychiatric risk, and or social network size. So the model would look something like this. I have a Y that is risk aversion, and I could include childhood trauma or parental income or psychiatric risk or social network size in my model. So I would use, let's say, a forward or a reverse stepwise selection procedure here, and it would say that the best model is a model that just includes childhood trauma and psychiatric risk scores. Now, essentially what I've done is I've said this is the best form of my model for explaining variance and why. I don't need the other terms. I've done a hypothesis test, but I haven't compared it against a null of the regression coefficients being 0. I've compared them directly in how they explain variance and why. So my conclusion is going to be that only childhood trauma and psychiatric risk are relevant for understanding variation and risk aversion. Now, the individual regression coefficients, beta 1 and beta 3, might not themselves be statistically significant from 0. That doesn't matter in this case. This particular form of the model is the best model out of all possible combinations of explaining variance and why. You can use this in cases where you have really complex relationships and you just want to ask the case for explaining variance and why writ large, as opposed to whether or not any individual regression coefficient is different from 0. It's a slightly different null, but it gives you a useful way of doing an interpretation question on what is essentially a prediction model analysis. Now, I want to end by explaining why we care about the difference between stepwise procedures and full subset procedures. Full subset seems like the most comprehensive. You're comparing all your models. So what? Why do I care about doing stepwise if I'm going to start just not comparing relevant things that might be relevant in my model? Well, as I mentioned, that for full subset selection, you have to compare 2 to the p models. Whereas for the stepwise methods, you're comparing 1 plus p times p plus 1 divided by 2 models. Then let's play this out logically. Let's say that I have 4 models, a model with 5 variables, 10, 15, and 20. For the full subset selection, I'd be comparing 32, 1024, 32,768, or 1,048,576 models for p equals 5, 10, 15, and 20 respectively. You see how the number of models literally exponentially increases, such that when I have 20 variables, I'm comparing well over 1 million possible models. Whereas doing the same model comparisons but with stepwise procedures leads to 16, 56, 121, and 211. So the stepwise methods improve speed dramatically as you get more complex models, as you're asking models with more variables. And if you're using, as opposed to what I showed in the lecture, if you're using, let's say, cross-validation for your model comparison instead of bias-adjusted criteria, doing a full subset selection with full cross-validation can take a lot of time. And if you've got way more than 20 variables, you're looking at an intense computational cost, whereas the stepwise procedures can get you pretty close with substantially fewer comparisons. The main take-home of this lecture is that model selection approaches allow for you to find the most parsimonious model for explaining variance in your response variable y, while accounting for model complexity. They allow for you to ask the question, what is the most parsimonious configuration of my model that is best at explaining variance in y, and directly assess that. And as I pointed out, it also allows for you to figure out the best possible way of asking which models or which variables are relevant. So it does, in some ways, a hypothesis test as well.